Hello and welcome to this week's edition of Video Notes. We're going to be talking about light again. So we previously have been working with light and measuring it as it relates to energy. We now will move into a more complex view of light. So light actually has three ways of behaving, and we call these the three models of light. Each model explains the behavior of light within a certain range of physical situations. So when the situation changes, some of the models don't necessarily fit with how light behaves, and that's why we developed the three models. Those three models are that light is a ray, that light is a wave, and that light is a photon. And they're called the ray model, the wave model, and the photon model. So we're going to start with the ray model. It's well known that light travels in a straight line. These straight line paths are actually called rays. Hence we have a light ray or a ray of sunshine. The example of this is the reflective properties of a mirror. So we can see from this image that light reflects off the mirror at an angle equal to an opposite of the angle that first hit the mirror. So it comes in at this angle and it goes out at that angle. I'm sorry, you guys can't see the arrow. So another example of this is we can see this perfume bottle is placed before two mirrors, and the two mirrors are placed at 90-degree angles. The image of the perfume bottle is fully reflected from the mirror on the right. It's fully reflected from the mirror on the right, and is also fully reflected from the mirror on the left. But because the mirrors are perpendicular to each other, so they're at a 90-degree angle from each other, and each have view of each other, so each of these mirrors can actually see the other mirror, they also reflect each other's light. So the mirror on the right has a reflection in it. This mirror right here is actually reflecting this mirror surface over here. And in the same way, this mirror on the left, back in this little corner here, is reflecting this mirror on the right. Now, lastly, we'll talk about the wave model, and the wave model is the most known and applicable model of light, like a light wave. Under many circumstances, light behaves just like a sound wave or a water wave would. Although it may seem counterintuitive, even laser light can best be thought of in terms of a light wave, as I will demonstrate in class this week. Now, you might be asking how light can behave as a ray and as a wave, and that's actually because light is a photon. And a photon is defined as being a quantum of electromagnetic radiation. And a quantum is the smallest discrete quantity of a particular form of energy. So a light photon is the smallest discrete particle of light. And another way of saying discrete is that it's one single thing, it's counted. It's just, again, it's another way of saying it's the smallest single unit of something. So when you guys see like a beam of light from a flashlight, you're actually seeing quadrillions of little photons screaming across the air, and that's what you're perceiving as light. So for right now, we will talk about the properties of light as a wave. And here is a picture from last week's video notes. And last week we referred to light, we related it to energy. And when I showed you this picture, I removed the references to frequency and to wavelength. So they're back again, and we're going to show you that what I'd like to point out is the relationship between frequency, wavelength, and energy. So over here with radio waves, the frequency is 10 to the fourth, so that's 10,000 hertz. Sorry. So 10,000 times per second is what the cycle is. The wavelength is also 10 to the fourth meters. So wavelength is about 10,000 meters long, frequency is 10,000 hertz. The energy is actually the lowest energy. So again, a high or low frequency, low wavelength, and low energy. Over here we have gamma rays. Gamma rays are very high energy, as you guys remember, if you guys want to remember the Incredible Hulk. Gamma rays also have incredibly high frequency, that's 10 to the 24 hertz. They also have a really, really small wavelength. It's 10 to the negative 16 meters. It's actually called an attometer, but because it's simpler to say 10 to the negative 16 meters, we'll stick with that. But what I'd like you to notice is that gamma rays have a very high frequency, a very short wavelength, and a very high energy. So again, for a recap, radio waves have a very low frequency. They have a very long wavelength, 10,000 meters, and they have the lowest amount of energy. Gamma rays have high frequency, short wavelength, high energy. Now, when we look at light specifically inside our spectrum, it's kind of the same thing. Over here we have red light, and red light is 750 nanometers for wavelength, and it's also some of the lowest energy. So if you remember the disc players that have red lasers in them, it's over here with low energy. Over here where we started getting into the blue and violet, this is where Blu-ray players are, and their wavelength is between 400 to 450 newton or nanometers. And again, it's on the more powerful, the higher energy spectrum of light. And it's, again, higher energy. That's where you start getting better definition pictures. You start getting better definition pictures, you start getting better sound quality. And I'm going to point out, we did this in class a few weeks ago. This right here, the symbol on the side is lambda. That is actually the symbol for wavelength, and we'll cover that more in class. Thank you guys very much for listening to these video notes, and I hope you guys have a good day.